demain.
All right, we're good now. Okay, so let's go. So there is 3 chapters in the course. So we went through chapter 1, which was a general introduction. Now we're starting chapter 2, which is about fundamental results. So essentially, we want to prove existence and uniqueness of solutions so that our problem is well posed. So I don't want to give you too much information and to lose you. So I'm going to try to focus on some key points. So those are the sections of chapter 2. So first we will start with some definitions and we will talk about maximal and global solutions. Then we'll go through theorem of existence. So there are 2 big theorems in this chapter. The first one is Cauchy-Peano-Arzela. And it's only a theorem of existence. There's no uniqueness. While the other one is the Cauchy-Lipschitz theorem, and this is a theorem of existence and uniqueness. All right, so this is the roadmap of the chapter. All right. All right, so first section, definitions, maximal and global solutions, and regularity. So now we're considering, sorry about that, we're considering a first order ordinary differential equation, but we add an initial condition. I'm sorry, I got a problem with the phone in my office. Okay. Okay, so this is usual. So you have the differential equation there, and you add an initial condition. So at time t equals 0. All right. And so this is an initial value problem, IVP. And so our general assumption is that f is a continuous function. And so usually f is defined for t which belongs to R and u which belongs to R to the m. But of course, at some points, f might not be defined. So the definition here is more general. Again, I'm asking you to mute yourself unless you want to ask a question. All right. So just this is clear. So just to say that by definition, we say that a function is a solution if it's differentiable and it satisfies the initial condition and the equation here. So that's the precise definition of a solution of our initial value problem. So all right. And so to start with, I propose you to think about a problem, an exercise. So first, so you know very well this equation. So it's a first order differential equation. And so you had an initial condition, and so solve this equation and think about on which interval the function, the solution is defined. All right. So yeah, you can do that. So I let you do that. When you have a solution, you tell me. So the solution of this equation, so you had an initial condition, and then you tell me where the solution is defined, for which t, all right? So I let you, and when you have a solution, you tell me. All right, so so basically you solve the problem, you solve the exercise, but let us go through it again and give more details about that. So first, yes, so this one, you got it. If you take ut equals u node exponential of t, then you get, so this is solution of the initial value problem. All right, and u is defined on R. So this corresponds to the first question. Now, now the second one. So the second one is just a little bit more complicated. Instead of u, I take u squared. So first, as you said, if I can remark that u of t equals 0 is solution of u prime equals u squared and u at time 0 equals 0. So this is a solution, but this is a specific one, right? And so u of t is defined for all t in R. So now let's assume that u node is greater than 0. Okay, so assuming that u is continuous, yeah, that's right, yes. So assuming that u is continuous, if u at time 0 is positive, this will remain through for a certain amount of time. So I can divide here, as I saw in the chat, I can divide by u squared, the both sides of the equation. And I obtain this. Okay, if I divide the equation on both sides, I obtain this. Okay, but now I recognize here this is the derivative of 1 over u. You okay with that? Are you okay with that? You should not. There's a problem here. So I say that the derivative here gives me that. Are you okay with that, or yes or no? Yes. Yes, a minus is missing. Okay, so this gives me and then I can take the integral between the time 0 and the time t, and I get u minus 1 of t minus u minus 1 of 0 equals t, which gives u minus 1 of t equals so sorry, it's minus t. There's a minus here. So this gives me this expression. And finally, I get u of t equals 1 divided by u minus 0 u to the minus 1 at time 0 minus t. Okay, but okay, and okay. So now if this quantity here is positive, so my initial value problem, it's at time t equals 0, right? It's at time t equals 0. Then from t equals 0, I can extend it to the right, positive times, or to the left, negative times. So I can see that this solution is well defined for all negative times, right? And for positive times, it's defined until t reaches the value u to the minus 1, 0. So then it explodes. So u of t equals 1 divided by, so my assumption is that at time t equals 0, I want this value. And so u of t, or u, but at this time, it explodes. So my solution is not defined for t equals 1 divided by u naught. So this is the case if u naught is positive. But if u naught is negative, then I can extend. So that's the difference. Now, what's the difference if u naught is negative? So if u naught is negative, all the computation is the same. But what can I do? I can extend my solution on the right. There's no problem. But on the left, for negative times, I will find, if I go to the negative times, I will find 1 divided by u naught. And then this is not defined. So now if u naught is negative, this is the same, the solution is the same. U of t equals 1 divided by But then I can extend my solution I start at time t equals 0. I can go to the right or to the left. And in the case where u node is negative, I can extend it as far as I want to the right. But on the left, I cannot take the value 1 divided by u node. This makes infinity. So I have to stop here. And so note that here in this case, all right. Okay, just let me I'm waiting for you, right? So just let me draw some picture. So let's here I represent the time, and here I represent the value. So here is the time 0. So at time 0, my solution here takes the value u node. And so I start from here. In this case, u0 is positive. And when I reach this value, it goes to infinity. And here, when t goes to minus infinity, this is well defined and it goes to 0. And here it explodes. Well, if u node is negative, then I got that. All right. So of course, at time t equals 0, u of t equals u node. So what was the point of this exercise is to illustrate that you can that the solutions are not always defined on the whole real line. all right? But you can extend solutions up to a maximal interval. And that's the definition here. It says that you can extend some solutions, and then you call it, in this case, in the definition written here, U2 is an extension of U1, right? So that's typically the case in the question 2 of the exercise. We start with a solution at times t equals 0, then we extend it on the maximal interval possible, all right? Okay, so we say that the solution is maximal if it cannot be extended, right? And there is a proposition is that every solution can be extended up to a maximum interval, all right? So I'm not going to prove that. Basically, these 3 chapters are inspired by a few books, but the closest is the book of Jean-Pierre de Mailly, but I will give you the reference at the end. So there's a proof in there. I'm not going to prove that. All right, now a global solution is, for example, in our case, our function f is defined for all t in R. This doesn't mean that the function u will be defined on R. Oh, okay, thank you, thank you. Sorry, who cannot see the screen? So you should be able to see it. So if there's only one person who cannot see the screen, so the problem is with you. All right, so no, so your problem is Mrs. Younes, the problem is with you. Yeah, thank you, Thomas, thank you. All right, so as I was telling you, so a solution is said to be global if it satisfies the equation on the whole interval of where f is defined with respect to the variable t. So, for example, again, the exercise 2. In the exercise 2, the solution u equals 0 is a global solution, but the others are maximal but not global. All right. Okay, this is a definition. All right. Okay, now regularity. So our basic assumption is that f is continuous. But if f is more than continuous, you have more regularity. So the theorem is, so if f is of class C0, then u will be of class C1. This is a theorem. And if f is of class CK, then u, the solution will be of class CK plus 1. All right. Well, I'm I'm not going to prove that here, but you can do it as an exercise. All right. I have the proof right on my notes, so I will give you the notes on the appropriate time. All right. So okay. So basically, the idea relies on the composition of functions. All right, so let's go on. Okay. So it's time, I guess it's time for a little break. So we are now moving to the existence theorem of Cauchy-Peano-Arzela. So this will take us some time, so we are not going to finish it today, but we are going to provide a key theorem today. All right. So first of all, we can remark that our initial value problem is equivalent to this integral equation. All right. So if you assume that U is continuous, then this is the fundamental theorem of analysis, that then you can take the derivative of that. All right. So if U is equal to that, it's differentiable. And when you differentiate it, you find that U prime equals f of t U of t. All right. On the other hand, if you assume that U is a solution of our initial value problem, and then you integrate the equation U prime equals f, and you get that. So there is an equivalent formulation of the initial value problem as an integral equation. All right. So if we find that a function U is continuous and satisfies this equation, it's a solution of our initial value problem. All right. So again, I just explained the proof. You can write it as an exercise. So now, so the proof that I will provide from the existence of a solution of the initial value problem relies on the convergence of a sequence of functions, and the limit will be a solution of our initial value problem. So here we are going to provide a theorem in this framework, right? So we, as a general fact, we consider a sequence of continuously piecewise differentiable functions, which means what? This means that, so I will call them UP, So this is a function. For each p, up is a function. And so I consider here an interval 0, it's my initial time, and the final time t, right? So I assume that for each p, up is a continuous function on 0t, and that it's C1, but piecewise. This means that there exists some division of my interval 0t, and my up is C1 on each interval tk plus 1. All right? So my function up is continuous, and it's differentiable and with a continuous derivative on intervals. All right. I can, if I want to, I can draw some picture here if you want. So this means that here, let's assume that I have my interval 0 and t here. And for each p, so the function is continuous. And is derivative on each interval. But here, maybe the derivative at left, it's not the same that the derivative at right. All right. So this is a typical example of a piecewise, continuously piecewise differentiable functions. All right, and then, so this is for one p. But then I consider here a sequence of such functions. All right? Okay. Oh, okay. I made some assumptions on the sequence UP. First, I want that UP are bounded. So there is a constant M such that for all P and for all T, the norm, so this is the norm on R to the M, of UP of T is less than the constant. So there is a uniform bound on the sequence for all P and for all T. All right? And I further assume that, okay, you know, I chose the letter U for the sequence. So the sequence for each P, it's not a solution of my ODE, of my initial value problem, but it's close to a solution. And in particular, I assume that there's a mistake here. There's no T here. It's a mistake. All right. I can just, sorry. I'm just going, oh. Sorry, there's a bug here. So here. Okay, so I assume that. So what's the idea here? It's that UP is not a solution of the ED, but it's close to. So if UP was a solution of the ODE, here this will be 0. So it's not 0, but it's a small number, and it goes to 0 as P goes to infinity. Is that clear? So you choose the norm you want, but to fix things, let's choose the usual norm, the Euclidean norm. So I'm working on a finite dimensional space, which is R to the M. So it's let's choose the Euclidean norm. All right. You can choose the norm you want because all the norms are equivalent in the finite space. All right.
Sorry, teacher.
Mm-hmm.
What are the conditions about that epsilon?
So my epsilon is aimed to be a small number. The condition is that epsilon p is going to 0 as p is going to infinity. So epsilon p is a sequence of positive numbers that converge to 0. So the idea is that epsilon p is small.
Yes, but it's for all epsilon positive, or what exactly?
No, there exists. There exists. So the idea is that we assume that we consider a sequence of UP, and we assume that there exists a sequence also of positive numbers epsilon p, such that epsilon p converge to 0.
It's a positive number?
Yes. Yes. Okay. So, is there any question? Okay, so we assume that we are given a sequence of functions. I called them UP. They satisfy these two assumptions with epsilon p, a sequence of positive numbers that are converging towards 0. Okay. So now, with those assumptions, the following theorem holds. So now, let's assume that the sequence UP is converging uniformly towards a function u on the interval 0t. Then u is a solution of the problem. All right. So what's the point of that? Is if I am able to construct such a sequence, I come back here, and if my sequence converges uniformly to a function, then this function is a solution of my ODE and of the initial value problem. Is that clear? So what we are going to do the next lecture, we are going to construct such a sequence. But now we are just dealing with the fact that if such a sequence exists, then the limit u is a solution. Is that clear?
Yes.
All right. Does somebody want to discuss, to contest? Okay, you are okay with that? So prove it. Okay, so prove it. Prove that. Prove the theorem. We're going to prove it. And that's we are going to do until the end of the lecture. So I let you 5 minutes. 5 minutes, think about it. Then I come back with an exercise. So I let you 5 minutes. If you have a question, I'm here. So we want to prove that UP of t minus u naught minus the integral between 0 and t of f s up of s ds is less than t times epsilon p. That's what we want to prove. All right. So, but well, so UP is piecewise differentiable, continuous. I can write that. And at time 0, UP of 0 equals U0. So I can do that. So it's T, right? I have that. I can write that. So for sometimes the UP prime is not well defined, meaning that you have some limit at the left and some limit at the right, but it doesn't matter. I can write that. Okay, so this in turns implies that so I just replace in my first line So this is equal to that. Which is equal to okay. But then the norm of the integral is less than the integral of the norm. So this will be less than but this is less than epsilon p. It's one of the assumptions. So finally, I got that. So now we have that up of t minus u node minus the integral between 0 and t of f s u p s yes is less than t epsilon p. So since up converges uniformly towards u, for all t, we have that up of t converges towards ut as p goes to infinity. So if the integral between 0 and t of f s u s yes converges towards then, since the norm is a continuous application from Rm to R, then we will get that by taking the limit when p goes to infinity, we are going to get u of t minus u node minus the integral between 0 and t of f s u s ts equals 0, which means that ut equals u0 plus which means that u is a solution of my initial value problem. So to get the proof, we need to prove that this is true. All right, so that's what we are going to do now. So we are going to prove that. And to prove that, it is sufficient to prove that so now we are going to prove that integral between 0 and t of f as u p s ts converges to and so to do that, it is sufficient to prove that the sequence of functions up when p belongs to n converges uniformly towards fsus. But that's true. What we know is that S belongs to 0t, and for all p, for all s, the norm of up of s is less than m. And so this implies that f so we know that, so it's not exactly that. So it's just so, but since f is continuous, f is uniformly continuous on the compact 0t times 0m. It's not, it's the ball, right? The closed ball, okay, which is compact. That's why it's uniformly continuous. You said that. All right. So now, okay, so this, I've already said all of that. Now I'm going to write what's the meaning of uniformly continuous. This means that for all epsilon greater than 0, there exists a mu which depends on epsilon, such that for every t so I'm going to write like that. For every t s belonging to 0t, and for every I'm going to write that v W belonging to the ball, I will have that the norm of f s v minus f t w is less than epsilon. All right, but now sorry, I forgot the, so I can take that the I forgot the assumption. So the mu, you see, the mu is not here. So I went too fast. So if the distance between S and T and the distance between V and W is less than mu, then this is the meaning of uniformly continuous, right? Okay, now, once I have that, I will be able to prove that my sequence converges. Because now, but since UP converges uniformly towards U, there exists, let's say, capital P, such that UP for all S, UP of S minus U of S is less than mu. But if UP minus US is less than mu, this gives me this in turn implies that F S UP of S minus F S US is less than epsilon. And this is for all P such that P is greater than capital P, and for all S in 0G. So that's what I say to summarize. I used the here uniform. I use the fact that F is uniformly continuous and the fact that UP converges uniformly towards U. And this implies, now you see that this is this means that this is the definition of the uniform convergence. So this means that Fs of US P converges uniformly towards Fs US. And this ends the proof.